All right, guys, this is just going to be a quick review of Chapter 7. Not super in-depth, just hitting the highlights. So 7.1, integration by parts. We have the formula u dv equals uv minus v du. Okay, so that's the important one to know. And then also important to know as a kind of shortcut is this rule Liate, where this is logarithm inverse trig algebraic, I guess, trig and exponential. Okay, so the thing that's farthest to the left is usually our u. Okay, so for example, if I was looking at the problem, ln of x times x dx. This is an integration by parts problem, but what should be my u, what should be my dv? Well, I have an ln, that's a log, that's farther to the left than this x, which is my algebraic stuff. So I should let my ln of x be u, my x be dv. Okay, when I do that, I get ln of x times x squared over 2 I should get this integral. All right, you guys can check me on all of these. I'm just running through these problems pretty quickly, so don't, I might very possibly make mistakes on these videos. Feel free to double check me. Okay. One thing that's important to know about 7.1 is integration by parts multiple times. So this is common when we have like a power. Okay, maybe a higher power of our variable t. So this should be dt. So if I have t squared et to the dt, I'm going to need to use integration by parts multiple times. Let's say I have an algebraic and a exponential. So let's say the t squared should be my u, the et should be my dv. Okay, when I use that setup, I have t squared e to the t minus integral e to the t times 2t. Okay, then I get this integral, and again, I should let t be u. We usually want to kind of keep this, keep similar u's.
As I was saying, we usually want to keep our u. We don't want to switch what we're using as u and what we're using as dv throughout our problem. So if the t's are my u at the start, I want to kind of use the powers of t to be my u throughout. All right, so I should let in this part, I should let t be u and et be dv again. And when I do that, I get this. So not too bad, but I just had to use integration by parts multiple times. And again, please check me on these problems. If you're unsure, you might very well have done it right, and I might have done it wrong. Okay. Another common time we see integration by parts multiple times is when we have trig stuff. Okay, and then we have that special trick where, oh, you do integration by parts multiple times, and then I'm going to move something from the right side over to the left side. Okay, so if I try and integrate e to the x sine of x dx, let's see, I could let u be my sine and dv be my e to the x. So let's see, if I do that, then okay, so I apply integration by parts one time and I get this. Okay, now I use integration by parts on this piece. I say, hey, e to the x cosine of x, that's, let's see, I want to use cosine as my u, so dv would be negative sine. Okay, now notice I have this integral again. Okay, so let's, this integral is just this piece here. So let's plug this in. Let's rewrite our left and right side. Okay, now notice this is my original integral. Okay, so I'm just gonna move this integral over to the left side with my original integral by adding it to both sides, and I get 2 e to the x sine of x dx equals sine of x e to the x plus, let's see, did I do something wrong here? Yes, I did. Excuse me, this shouldn't have been sine, this should have been cosine, right? And let's see, it's going to be positive. Okay, this integral is still good. Okay. And we should end up with this. And then I'm going to divide both sides by 2. And then I need my constant of integration plus c. Okay. So again, we've used integration by parts multiple times. Now let's move on to section 7.2. Trig integrals. Okay, for section 7.2, there's not much to go over. These trig integrals are just u subs, really. We just have to know our table from page we have a couple tables, page 481 and page 482. And then we should also know the double angle identities. And just to be clear, what I really mean by double angle identity is that, let's see, cosine squared of x equals 1/2 1 plus cosine 2x. What about sine squared of x? Okay, we gotta know those. And then the usual trig identities like sine squared. And then what do we have? Tangent squared of x plus 1 equals secant squared of x, I believe. Okay. So just a quick example of these trig integrals. Let's say I wanted to do okay, looking at my table on page 481, I see that, let's see, when I have an odd power of cosine and an even power of sine, what I want to do is I want to split off one cosine. I want to write the remaining cosines as sines using my trig identity. And then I want to do a u sub where u is going to be equal to sine. Then du is going to be cosine. Okay. And my integral becomes, my sine squared becomes u squared. My 1 minus sine squared becomes 1 minus u squared. Then my cosine dx becomes du. Undoing my trigs or my u sub. I get this. And there are some cases where we could do our substitution either way, and we might get two different answers that they look very different, but in fact they're the exact same. They are equivalent. So in that kind of circumstance, either answer would be acceptable. There's no preference for one or the other. So there are sometimes multiple correct answers for these, but they're just equivalent answers in disguise. Rest of 7.2 is very similar. It's basically just u subs. What starts to get more interesting is 7.3, which is trig substitution. Okay, so what we have to know from section 7.3, first of all, we have to know our table on page 486. I wouldn't worry too much about the boundaries for theta. Okay, we have these inequalities for theta. For example, when I'm doing the a squared minus x squared substitution, it's for theta in between -pi/2 and pi/2. I wouldn't worry about that too much. Okay, that's a little technical detail that is not really going to come up in your problems. So just know the three different substitutions. So know the three the three cases. I'll say the three radicals. They're all these radicals, right? A squared minus x squared, a squared plus x squared, x squared minus a squared. Know the substitutions that go with each of these. Each has their own substitution. And then know the identity that goes along with this. So when we make this substitution, the top substitution, the identity that's important is 1 minus sine squared theta equals cosine squared theta. And let's see, when we make the second one, the identity we need to know is 1 plus tan squared theta equals secant squared theta. And then secant squared theta minus 1 equals tan squared theta. Okay, so we need to know this stuff, and then we need to be able to draw our triangles for each of these cases, all right? So case 1, for instance, okay, I have a squared minus x squared. That's telling me, however you guys draw your, maybe you draw your right triangle like this, whatever, it doesn't matter. I'll stick with this one on the left. Okay, so if I have a squared minus x squared, let's see, my hypotenuse, my longest side would have length a. If I'm using the substitution x equals a sine theta, that means my opposite side would be my x, and then this side would be my a squared minus x squared. Okay, this triangle, remember, is going to be important when we're undoing our trig substitution at the end of our integral. Okay, so we got to know the triangles. Those are all in section 7.3 as well. All right, so let's see a quick example of this problem. These problems. I'm not gonna, I don't think the problem's gonna be super complicated. We just have to know the basics. Okay, so remember, once we integrate, we get some sort of antiderivative. The antiderivative is going to involve like theta, and then some trig function of theta, right? Okay, and then we need to know how to undo these substitutions. All right, so remember that when we have theta, we look at our original substitution. We had x equals a sine theta, or a, we'll say a trig theta, right? Because we don't know which trig theta we're going to use. We look at our original substitution. First, we get the trig function by itself. And then we do the inverse trig function to both sides. Okay, so that's how we undo the substitution for theta when we have this theta term. How do we undo the substitution for, this trig stuff? Maybe our substitution is x equals a sine theta, but in this this antiderivative, we end up with like cosine of theta or something like that. We got to be able to look at our triangle and say, hey, what's cosine of theta? That's opposite over, or excuse me, adjacent over hypotenuse. So cosine of theta, a squared minus x squared over a, in this case, okay, in this particular case. All right, so let's see an example real quick. I have the problem okay, so let's see, what form is this? 9 is 3 squared, so I have really, okay, so I got a squared minus x squared, so I should use x equals 3 sine theta, right? That should be my substitution. Okay, and then what does that say about dx? Well, then dx will be 3 cosine theta d theta, right? So I'm going to plug this in for x everywhere I see it, and then I'm going to replace dx with this. Okay, so let's go ahead and do that substitution. I'm going to replace the x squared in the numerator with 3 sine theta, and then I'm squaring it. So my new integral is this. Rest is simplifying. First step, using my, well, I could bring the 3 out of this, right? Okay, start canceling. Let's see, this 3 cancels with this 3. I can pull a 9 outside. I got sine squared theta, cosine theta, d theta. Then this is divided by 1 minus sine squared. But for my identity, I know 1 minus sine squared is cosine squared theta. And this is really the only place it's important that theta is between pi over 2 and negative pi over 2. Okay, when theta's in this range, then square root of cosine squared is just cosine. We don't even have to worry about absolute values or anything like that. Okay, so my integral is this. The cosines cancel, and I end up with 9 sine squared theta d theta. Now I need to know my double angle identity. My integral becomes this. Okay, so my antiderivative's here. Now, how do I need to undo my trig stuff? Let's see, using the original substitution. Okay, let's see. If x equals 3 sine theta, then x over 3 equals sine theta, and theta equals sine inverse x over 3. How do I undo the minus sine 2 theta over 2? Well, let's see. Sine 2 theta, let's go back up to our, well, actually, we haven't drawn a triangle for this one yet. Let's see, so my triangle looks like this, roughly. We said x equals 3 sine theta, so this is my triangle. Actually, I should write it like this. Okay, so let's see. Remember sine 2 theta, this is another identity to know, is 2 sine theta cosine theta. Okay, so what's sine theta? This over this. So let's take this step by step. All right, so I need 2 times sine theta, which is x over 3, times cosine theta, which is 9 minus x squared over 3. That's all over 2. Okay, so that should be my antiderivative. Simplifying, let's see, these 2's cancel. And that should be my answer. Again, might be wrong. Went pretty fast, but that should be it. And the rest are similar. It's just different triangles, different substitutions. All right, so you just got to be able to apply the basic concepts. Now, moving on to 7.4, partial fractions. You got to know the 4 cases. So case 1, 2, 3, and 4. Remember what? That's when we have. Let's see. Case 1, distinct linear terms. I'm probably not even going to cover this section really because there's really no tricks. I will say maybe just a couple words. I'm not going to work any problems. So case 1, distinct linear factors. Okay, when we factor our denominator. Case 2, repeated linear factors, and so on. Okay, we got case 3 and case 4, so always know those as well. The only thing that, let's see, we need to be aware of is we need to be able to do all types of our, when we integrate our, when we break up our integral by partial fractions and then integrate, we're going to get usually 3 types of integrals, right? So how do I integrate something like this? Okay. So for example, let's give this is what I call this is my terminology, just an ln integral. Meaning when I integrate this, I'm going to get some sort of ln function, right? So let's consider 2x plus 4, for example. Okay. So if I make like a quick u sub, then I see that this thing, when I integrate, it should be 1/2 ln of 2x plus 4. Okay. So this is what I mean by ln type integral. Our antiderivative is going to be an ln. All right. So we need to know how to do this ln type integral when we have this linear factor on the bottom. What about an integral like this? Let's do another type of integral we might get is this arctan type integral. Okay, meaning when we integrate this, this is going to be like this is going to give us arctan, some sort of arctan. So this is looking a lot like, let's see, let's just rearrange it a bit. Okay, 1/16 plus x squared. Well, if I had 1/1 plus x squared, that'd be arctan. So can I get this to match that form? Let's see. Kind of similar with how we were working with series recently. I pull out the 16. I get this, right? And then I can say that's equal to okay, and then I can do a u sub. to get this antiderivative. All right, so you should know how to do this type of integral as well. And I think if you can do those two, you'll probably be fine. Oh, and then let's see. The only other one I think we would see is something like an integral like this. Well, to do that, you just rewrite it as 2x plus 9 to the -2, and then do a u substitution. Okay, and it's a simple u substitution integral. So if you can do those three types of integrals and know your four cases for partial fractions decompositions, I think you're in good shape. Section 7-8 would be the next section. Improper integrals. This is hopefully you guys have absorbed my harping on throughout the semester about being very methodical in how we write our integral, meaning if I have an integral from, let's say, 1 to infinity, 1 over x squared dx, if I want to evaluate this integral, the first step is to rewrite it as a limit, right? This is crucial. Okay, crucial to rewrite it as a limit. You're going to lose major points if you don't rewrite it as a limit. Then, okay, we're evaluating the limit, or excuse me, we're evaluating the integral inside the limit. So solving the integral inside the limit. Let's see. Integral of 1 over x squared. Well, x squared, 1 over x squared is x to the -2 dx. Okay, this integral is this, right? Okay, then plugging in our bounds. Okay, until we get our limit as simple as possible, and then we evaluate the limit. Okay, and then we get this number at the end, we get the number 1, but we're not done yet. Okay, so we say we need to have this wrap-up sentence, kind of like with series. We need to say integral is convergent and so we have this. Once we say it's convergent, we can say, okay, this integral is equal to that. As far as improper integrals go, okay, we've seen the simple case of an infinite bound. We also need to know how to deal with negative infinity to infinity. Okay, remember we're going to have to split this up into two limits. Usually one will be from 0 to infinity, and then the other one will be negative infinity to 0. Okay, and we need to do each of these like we did the first case, right? We say limit as t approaches to infinity for this one, and maybe if we could do t, or we could do, just to make it clear that we're talking about a different limit, we could do limit of some other letter like s. Okay. And then improper integrals, we also have the case where we're talking about functions that are not continuous. Like we could go back to 1 over x squared. Let's see. So for I said 1 over x squared on the interval 1 to infinity, right? Well, on this interval, our function's continuous. But what if I did negative 1 to 0? 1 over x squared. Okay. Now this function is not continuous at this endpoint. Okay, so again, I need to consider it as a limit. And I need to go through my steps the same way and see if my integral is convergent or divergent. And in this case, I believe it's going to be divergent. Okay. So you guys, again, can check me on that. All right, but other than that, other than this way of writing our integrals as a limit, not too much new in 7-8. All right, so I think that kind of wraps up chapter 7. I'll do a short little talk on just 8.1, which is the only section of chapter 8 we did in the next video.